Okay, so given that we've just passed the hour, I think we'll get started. So welcome everyone to the second running of the Science Behind the Image competition webinar. We ran the first one of these 2 weeks ago and we thought it was very successful. What we'll be looking at today is three entrants for the image competition that happened at the end of last year. And we've asked them to come and give a few more words about their submissions and discuss some of the science and the imagery that they produced for that competition. So without further ado, I think we will start with our first presentation from Alexandra from the University of Birmingham, Department of Civil Engineering. Alexandra, if you're ready, could you share your screen?
So, hi everyone. My name is Alexandra Monka and I'm a second year PhD student at the University of Birmingham. So today I'll talk a little bit about my work into CFD simulation of airborne pathogen transmission in indoor spaces, which led to the creation of the winning image of this year's competition. So during any expiratory event, we release a warm, buoyant jet of air in which particles of multiple sizes are suspended. So by nature, this is a multi-phase flow problem. So in terms of just the jet dynamics, what we have is initially when the exhalation is released, we have a momentum-dominated region as the exhalation process begins and is established. And then at a point where the momentum and the buoyancy are comparable, what we get is the jet begins to curve upwards, and then past that point we have a buoyancy dominated region. So the particles that are suspended within this jet, because of their different sizes, they will behave differently. So the small particles, which are known as aerosols, are those that will remain suspended within the jet and they will be carried with the air currents. So essentially they will behave passively and spread for however many meters the jet ends up traveling. And those particles will cause infection by inhalation. In comparison, we have the larger particles, which are just too heavy to remain entrained within that jet. So what will happen is those will fall out pretty quickly out of the jet and they won't travel as far. So those can cause infection via impaction, whether that's on the eyes or the mouth if you're standing close enough to someone who would be speaking or coughing or sneezing. So in the first part of my PhD, I looked at the effect of temperature on the transport of exhaled particles while a person is speaking. So depending on the ambient air conditions and the temperature, the jet will behave differently in the buoyancy dominated region. So when we have isothermal ambient air conditions, for example, a room at a constant temperature of 20 degrees, this jet will continue to travel upwards. But when we have thermal stratification, that being different temperature gradients in a vertical direction, what happens is this jet no longer continues rising upwards, but it will start oscillating about something called the lock-up height. And of course, we always have the pathogen dispersion. We have those aerosols and bigger particles suspended within this jet. So depending on the path that this jet takes, the pathogen dispersion will be different. And this highlighted region here, in thermal stratification, as you have the oscillation about the lock-up height, this can become a danger zone, if you will, because the lighter particles that are able to stay suspended within the jet, they may concentrate about that lock-up height. So what we want to know is, how does thermal stratification affect the risk of airborne cross-infection? And in particular, we have some questions that we want to answer. So which particles will be locked up in the breathing zone, and which temperature gradient do we need for that to happen? And how much will the pathogen concentration increase by in thermal stratified conditions compared to isothermal air conditions? And also what we want to know is, what is the effect of thermal stratification on different sized particles, because they won't all behave in the same way. So is there a threshold up to some aerosol diameter that they will remain locked up versus a continuous fallout of the jet, things like that. So to answer these questions, we run CFD simulations. So we use our own in-house code called Multiflow 3D. And the code uses MPI parallelization. And this is all of these simulations are large eddy simulations with a Eulerian Lagrangian approach. So the air is modeled in a Eulerian frame, and the particles are modeled with a Lagrangian particle tracking algorithm. So each particle is tracked in space and time, and we can then get a detailed view of where those particles are in a given scenario and in a given room under certain conditions. And from that, we can figure out what is the concentration of these particles and how does it change. This algorithm uses two-way coupling, and all of our visualizations are done using TechPlot 360. So this image was the one that I entered into the competition. So this image shows the aerosol dispersion in a room during talking for 3 minutes. So this is at the 3-minute mark. And this shows how the particles disperse in the isothermal conditions. So here the room is at a constant temperature of 20 degrees, and then we have this buoyant jet that is being constantly released as the person speaks. And as you can see, the larger particles, the red and the yellow, they fall out pretty quickly, but the aerosols, the blue and green particles, they spread throughout the room. And you can see a lot of them are near the ceiling, and then as the jet hits the ceiling and spreads further into the room, it takes those aerosols with it all the way until all the corners, essentially. And here is the video of that same case. So you can see it's quite a lot of particles, and what we're trying to do is figure out which scenarios make the situation worse in terms of pathogen concentration and where that concentration is, as it's important to know both in space and time how that concentration evolves and what we can do to reduce it, and essentially where in a room are like the hotspots, because the concentration won't be uniform everywhere. So we need to know where in a room is the most dangerous situation. So thank you for listening, and I'll be happy to take any questions.
Thank you very much. That was very interesting. We have one question immediately from Andy. Are larger particles that impact generally more infectious than smaller inhaled particles, or is the infection rate similar?
So right now we are just looking at the concentration of the particles. So essentially we don't assume that, for example, larger ones will be carrying more than the infectious material than the smaller ones. What we're looking at is just the concentration. So in terms of, if you look at the concentration based on the volume fraction, because the larger particles are so much bigger than tiny aerosols, 1 micrometer compared to 100 micrometers, their concentration will be higher, just because even though there's less of them, they're so much bigger. But what we don't know is that would only work on the assumption that each particle carries the same viral load, which might not be the case. So what we need to, that's another one of the questions that needs to be answered, is which particles carry more of the viral material. Can we assume that all of them carry the same, or is it like, for example, aerosols actually carry more? So this is something that still needs to be answered, and then based on that we would be able to translate this into our concentration.
Thank you very much. Any other questions from the chat? As Andy's commented, this depends also on the specific pathogen, and it'd be interesting if you ever had a plot where this was then modeled. If you knew an infection rate both in pathogen and droplet size, you could then also show that in a similar way. It would be very sort of the most dangerous place to stand in a room. That's a future question, I suppose.
Yeah.
Okay. If we don't have any other questions in the chat, Demantis has raised his hand. Who'd like to ask a question? Go ahead.
Yeah, can you hear me?
Yep.
Okay.
Yep.
Yeah, so thanks for an interesting talk. And in regards to the particles rising up, how long does it take for the room to kind of diffuse after? Because as it reaches up, it basically reaches the ceiling, and at some point the room still has to kind of fill up. So what's the time frame for that to happen?
So the results that I presented, that was for 3 minutes. So after 3 minutes, I guess you can say the room's pretty well filled with aerosols. So it depends on how much of the room you'd be looking to fill. I'd say for the conditions that we presented, so that was for speaking, and during the 3 minutes, a decent size of the room is already filled with aerosols. So I would say a couple of minutes is all it takes. Of course, it depends on how long it takes, like how many viral loads, like how much viral load you need to actually get an infection. So, you know, for example, this may not be enough aerosols still in the room to cause an infection. We don't know that.
Yeah, that makes sense because people will have different viral loads in themselves, I think. And
Yes, yes.
okay, yeah, that answers my question. Thank you.
Okay, if there's no other questions, thank you very much for the lovely talk, and we'll move on to our next speaker, which will be Demantis himself. So that's
Thanks.
a nice segue. So Demantis will be speaking about ray traced cloud development simulation videos. He's coming from the University of Leeds.
Yes, so I am a PhD student, first year in University of Leeds, and this work here that you see is actually right before I started my PhD. It was an internship that I did with Earth and Environment at Leeds University, and this quite nicely led to my research because nowadays it's quite interdisciplinary between the School of Computing and Earth and Environment. And essentially, this work was visualizing the models that atmospheric scientists have made. And this is also using large eddy simulations. And the models themselves are of Lagrangian nature. So the parcels are following an underlying grid from which they get the atmospheric properties, and they are propagated over time, and the cloud evolves. And in this animation, you can see the cloud as it evolves over time. And this first frame is the first few instances. You can see the cloud and the cap forming. And as the cloud progresses, the development is fueled upwards, and the edges at the boundary curl up quite a bit. So the initial challenge was to, because these simulations are run at higher resolutions than ever before. So this cloud, for example, is 1,000 by 1,000 by 1,000. So it is quite a bit of data, and scientists always want to evaluate it not only in a statistical sense, but also visually. So this is one form of evaluation, just seeing how the simulation would look like in sort of realistic settings. And ray tracing is one method which can, in fact, simulate how light moves through a cloud. And as the rays of light move through the cloud, they get attenuated, and you can actually see the bright regions and the shadowed regions in the cloud quite clearly, because the ray tracing algorithm sums up the light contributions based on the neighboring regions as it passes through the cloud. And these visualizations were done in a software called PowerView. And the key idea was to use high-performance computing systems to allow us to do this sort of work in parallel, and using video graphics processing units to deal with all of this data volumes that we currently have. And the new simulations will be running at even higher resolutions. So these clouds are 1,000 by 1,000 by 1,000, but we are not limited in a way because we already ran a few with 4000 cubed, and this is a more high resolution image which shows only one frame of the cloud, and you can see it's a bit more detailed than the ones shown in the video. So yeah, I think this is a brief introduction on this.
Thank you very much. Does anyone we can have any questions? I can't see any in the chat right this second. I have a couple myself. So during the video, you see this sort of jumping progression as the cloud evolves. Sort of, do you have an idea of like time scale you'd expect? I mean, I suppose this depends on volume and what you're trying to simulate in real life, but what are the gaps sort of representing in terms of simulation steps?
Yes, so the gaps here are just because well, they model the cloud in time, and for the sake of video, we wanted to capture the key moments in the cloud's development. So in fact, what could be an improvement of these videos is actually making it smoother, as you suggested. But I think in this case, our limitation was the amount of data, because for each frame there is a scalar field. So I think these are only 7 time steps. So it's kind of 7 separate data sets. And if you wanted a smoother animation, we would need perhaps 60 time steps. And the current limitation was fitting that amount of data on high performance clusters storage. But yeah, indeed. So here you see the 7 key timestamps which we chose that include some kind of key stages in the cloud development.
So we have one question from David. What determines the final shape of the cloud structure? Is this based on a set of initial conditions, or is it ultimately random, or is it reproducible? If you set the same conditions, do you produce the same cloud exactly each time?
Yes. So I would say that I understand why you'd think it could be random, because weather systems and larger simulations are quite chaotic in their nature, but that also means that some stochastic methods would be used. But I think in their case, if the initial conditions were set in the scope of a model, because that's the conditions they know about, you would get the same output, which might not be true in nature, because there is so much more parameters that humans are not aware of. And even though if you observe a cloud at the same atmospheric conditions, it might develop very different in nature. But in this scope, the scientists have pinned down specific parameters. Then by setting those parameters, you would get the same cloud.
Thanks. So a question from Andy. Are you able to utilize something like GPU, NVIDIA GPU hardware specifically to support the ray tracing you were doing to do the visualizations, or in your research, or have you explored this in any way?
Yes, exactly. Because so GPUs just allow massive parallelism, and for a problem like ray tracing, essentially what the key idea is for each pixel in your image. So pixel is just a picture element, and you can think of it as a square on your image. And for each that square, you compute the lighting contribution. And what GPUs can do, in fact, is by looking at each pixel, we can see that it's independent on each other. And with a GPU, you can massively scale your operations that way, because for each pixel, it will compute the lighting contributions. And there are more sophisticated ray tracing algorithms which are kind of neighborhood dependent, but still, if you look at the individual pixels, it's quite an independent operation on itself. So that way we can massively speed up the rendering process.
Thank you very much. I think we will move on to our final speaker today, which is Dr. Nicholas Bempoulis, who's from Imperial College London. He's going to talk about flow within and around large wind farms.
Right. Okay, let me get started then. I'm gonna briefly present a work that's related to the image that I submitted, entitled Flow Within and Around a Large Wind Farm. Now, a key word here is the word large, right? So here is a photo of the first offshore wind farm that was ever built. That's somewhere off the coast of Denmark. You can see this is just a wind farm that has just 11, if I'm not wrong, wind turbines. Right, so this is a very small wind farm, we can say. Nowadays, which is about 30 years later, this is a photo from one of the largest wind farms that exist. We're talking about wind farms that are now consisting of more than 1,000 wind turbines. We cannot see them all in this photo, of course, but we're talking about wind farms that are massive in size. And why are we interested then? What's important? What's very interesting when we are talking about large wind farm flows is that we are no longer just interested about the scales here that I show, not just about the airfoils and the wind turbine scales, but we are talking also about wind farm scales and atmospheric scales that influence the production, the power production from the wind farm. Of course, it's not just the atmospheric wind influencing wind farms anymore, but it's also the wind farms that influence the atmospheric flow when they become very large. Right, of course, when wind farms become very large, then we have a very big problem to tackle, because the smallest scales of turbulence around the airfoil remain the same, but we also have to consider the very big scales of the atmospheric flow where the wind farm is embedded in. Right, so what are we going to do about that? We're going to some numerical simulations using a flow solver called XCompact 3D, which is open source and solves the Navier-Stokes equations that govern the flow of fluids. Right, XCompact 3D can work either in a direct numerical simulation mode where there is no turbulence model, or in this case where we have atmospheric flows, we are using turbulence models, and we do large eddy simulations. Now, XCompact 3D scales with up to 100,000 cores, and soon it will be supporting GPUs as well. It uses high-order discretization schemes and a direct solver in spectral space for the Poisson equation. Now, it combines overall the flexibility, let's say, of general purpose solvers, but also the accuracy of academic frameworks. So this is the picture that I submitted. This is the flow within and around a large wind farm consisting of 25 wind turbines. So it's somewhere between the two, let's say. There are 5 rows of wind turbines with 5 in each column as well. And we can see the flow with very much detail here. What we actually see is a volume rendering of the velocity, highlighting the regions of reduced velocities that is downstream, typically, of the wind turbine, where the flow has decelerated. What's very interesting to see here is that we are able to see detailed visualization of the interactions between different turbine wakes, but also we're able to see how atmospheric turbulent structures impact and interact with those from turbine wakes. Lastly, what's very interesting to observe here is the wake meandering. So we can see that some of the turbine wakes are directed differently compared to other ones. So they're, let's say, yawed in certain directions, demonstrating the highly turbulent and unsteady nature of the wind farm flow. Now, here, just to demonstrate, just to convince you of how turbulent the flow is, here I composed a video of a much smaller wind farm showing you the interactions of the atmospheric wind with the turbines, with the wind turbines. Right, so what can we do other than visualizing the flow with such big simulations? We can actually gain a lot of insights regarding the processes and the exchanges that take place between the wind farm and the atmosphere in the form of parametrization of certain coefficients that are relevant to low-order models for wind farm flows. Alternatively, what we did with the simulations is trying to reduce the problem of wake turbine interference, which is particularly important for wind farms as it reduces the power output that they can yield. So when trying to minimize the wake turbine interference, what we're trying to do is maximize the power that the wind farm produces. So there's typically two ways of doing that. It's either positioning the turbines in a way that their wakes do not interact, or steering the turbines by misaligning them against the wind so that we redirect the wakes, again wanting to do the same thing, basically minimize the impact between upstream turbine wakes and downstream turbines. Again, with such simulations, we have done a data-driven optimization of wind farm layouts and turbine misalignment angles. And what we found is that we are able to resolve and exploit this complex flow phenomena that I talked earlier about. So wake meandering, local speedups, or wake-to-wake and wake-to-atmosphere interactions to deliver increased wind farm performance. Right, so that was a very brief overview of, let's say, the science behind the image that we've been doing here at Imperial College. And I'd like to thank you for your attention. Happy to hear any questions.
Thank you very much. We have one question from Just. Are the turbine blades spinning in the simulation? If not, what effect would you expect on the simulation if they were actively rotating?
In the simulations in this image, they are spinning, yes. The effect is mostly, just to answer completely, there are some alternative ways of parameterizing, let's say, the effect that the wind turbines have on the flow. And by some less accurate parameterizations where the blades do not rotate, but are represented somehow as porous objects, the effects are mostly on the near wake. So in the regions here that you can see with red. In the far wake, the green or gray, however you call it, whatever color that is, typically the rotation does not matter there because the wake has gotten to a state where it's mostly affected by external flows as well. So It's only about resolving the near turbine wake. That's the only difference, really, when blades rotate or not.
Thank you. One quick question for me, in terms of the way you've colorized this image,
Yep.
what are you using to trigger the sort of intensity? Obviously, darker reds is more turbulence, but how are you sort of quantifying that?
Right now, I need to remember exactly. I cannot give you a definite answer because I can't recall the color map. What I would say is that by red, it's probably regions of reduced velocities.
Okay.
Yeah, I think that's it. But again, I'm not entirely sure about the answer that I'm giving you right now.
So a question from Dementus, is the impact on the neighboring turbulence minimal at these chosen distances between them? So is how much effect are the turbines having on each other at these sort of distances you're displaying here? Obviously, we can see interaction of the wakes still reaching the next turbine. But is that a significant effect?
So I'm just stop sharing so I can read the question because I missed it. No. So in the picture that I was showing, it was just a regular layout where turbines were equally spaced apart. So this was not a result of an optimal, let's say, design with minimal interference.
Okay. Thank you very much. I don't think we have any more questions in the chat. And if that's everything, I just would like to thank all three speakers again for three very interesting talks and discussions on the imaging features for the competition. And thank you again for agreeing to speak to us today. If that's everything, I think we'll close the webinar here. Thank you everyone for joining.